Alright, a couple more things to note about polynomials. A polynomial equation of degree n has at most n distinct roots. Now, a polynomial equation is very similar to a polynomial function. The only difference is the equation, you set it equal to 0. And so instead of calling them zeros, now we call them roots. So polynomial equation of degree n has at most n distinct roots. In addition, if a plus bi, this complex number, a plus bi is the root of the equation, so is what we call the conjugate a minus ba, a minus bi. So if that complex number a plus bi is a root, then a minus bi must also be a root of the equation. In terms of zeros, it would be the zero of the polynomial. Now, the fundamental theorem of algebra, which is listed here, is why we can say this first point here. It says here, if a function of a polynomial, if f of x is a polynomial of degree n, and n is greater than or equal to 1, so degree 1 or greater, then this equation, f of x equals 0, this polynomial equation, has at least one complex root. And it can be shown that actually we can find n complex roots. Now don't confuse complex with imaginary. Complex includes imaginary and real. So what we're saying is this polynomial has at least one real or imaginary root. And this allows us to say that we have actually n distinct roots, at most n distinct roots of a polynomial of a degree n. And it also brings us to what the final theorem, it also brings us to another theorem called the linear factorization theorem. So the linear factorization theorem, which is the result of the fundamental theorem of algebra, tells us if I have a polynomial of degree n, an times x to the n, and so on to a naught. Remember, n is greater than or equal to 1. That's my degree is greater than or equal to 1, and n, the lead coefficient, is not 0. If we have a polynomial of degree n, then it could be written as a product of factors. An, lead coefficient, times x minus c1 times x minus c2 all the way to x minus cn. So we're going to have n factors. And note that c1 through cn, they are complex numbers. So that is a result of the fundamental theorem, which tells us there's at least one complex solution. So we found here that actually there are n complex solutions and n factors. But these c1 through cn are actually the zeros of the function. They're what make this function zero, and they're not necessarily real because they could be imaginary. Complex numbers include real and imaginary, and they're not necessarily distinct. So they could be the same if there's multiplicity on a zero. Some of these could be the same. So what this allows us to do is form polynomials. So let's take an example. Suppose we want to find a polynomial of least degree with these zeros, the -2, 3, and 4. So what this is telling us is that, well, I could find a polynomial of least degree, degree 3, because I have 3 zeros, and the way I can form that polynomial, we should actually say find a polynomial, because there's probably many, but one of them with least degrees, we can just multiply the factors. So we take each of these numbers and subtract them. So I have x minus minus 2 times x minus 3 times x minus 4. And this minus minus becomes a plus. And so we multiply those out, and if we multiply those out, what we end up with is x cubed minus 5x squared minus 2x plus 24. So that's our polynomial, a polynomial with -2, 3, and 4 as the zeros of the polynomial. Let's take another example of this one. So here we're asked to write a polynomial of least degree with zeros 1 and 1 plus i. Now you might think, well, okay, we have 2 zeros, so we're going to have a polynomial of degree 2. But actually there's a zero missing. Remember that these imaginary zeros, this is 1 plus i, they come in pairs. So 1 minus I is missing from here. It wasn't given to us, but we have to know that, okay, there must be a conjugate pair to this one. So we actually have 3 zeros, so it's the degree 3 polynomial. So from our linear factorization theorem, we know that this polynomial f of x of least degree can look like this. Well, let's leave the lead coefficient as 1, and then we write all our factors. These are our zeros, so we subtract them from x. So I have x minus 1 times x minus 1 plus I times x minus 1 minus I. And then if you take out the parentheses here, these signs will switch in the middle. So we're left with x minus 1 times x minus 1 minus I times x minus 1 plus I. Now let's multiply this out to simplify it. You may know, well, this might be a complicated product, but actually what we have here is we have a difference and a sum. If I isolate x minus 1, in each of these here, x minus 1 and x minus 1, we have a difference and a sum. And you may remember that a minus b times a plus b gives you a squared minus b squared. So a minus b times a plus b gives you a squared minus b squared. So similarly we could do that here. We can see that we have x minus 1 squared minus I squared. And then we can bring down the x minus 1. And so we have this product. So let's expand this a little bit. X minus 1 squared becomes x squared minus 2x plus 1. And then minus I squared. And then times an x minus 1. Now what do we do with this I squared? Well, you might want to note that I is equal to the square root of negative 1. And so I squared is going to be the square root of this root squared. You square a square root, you just get what's underneath, negative 1. That means this negative I squared is actually negative 1. And so actually we're going to add these two here. And so I have x squared minus 2x plus 2, because 1 plus 1 is 2, times x minus 1. And finally we multiply these out, and we end up with x cubed minus 3x squared plus 4x minus 2. So this polynomial, x cubed minus 3x squared plus 4x minus 2, is a polynomial with zeros 1, 1 plus I, and 1 minus I. And you can graph this to verify that this actually has one real zero at 1, and then these two zeros can't be seen on the graph, they're imaginary. So if we put that in our calculator under y equals, we're going to put in x cubed minus 3x squared plus 4x minus 2. And then we hit zoom 6 for the standard window. We get this cubic function here, and we could zoom in, but we could see that the zero occurs, the real zero is occurring at 1. So 1 is our real zero, but we should have 3, so the other two are imaginary. To find this zero, we go second trace, 0, enter, scroll to the left of the 0, enter, scroll to the right of 0, enter, enter again, and we see the 0 is 1. But that's the only real zero. But then we know there's two other zeros. So how do we find the other two zeros of a polynomial if they're not showing up on the graph? Well, that's something that involves some algebra, which we'll see.